Many chemical reactions are reversed, and we show that with this double-headed arrow. So the reactants can go to products, but products can also go back to reactants. And because of that, there are various ways that we deal with the amount of reactant or product being produced. We calculated with stoichiometry the amount of a product that might be produced given a certain amount of reactant. That assumes that the reaction goes completely to products, 100%. Some reactions do go essentially 100% to products, but not all of them. So there's this whole other consideration that we need to take into account to understand better how much of a reactant or product is being produced or being needed to get a reaction to optimize various reactions. So let's look at writing the equilibrium expression for these reactions. And so the equilibrium expression is a mathematical way of measuring how much a reaction shifts towards the right, the product side, or to the left, the reactant side. And the expression, the generalized expression, is shown here. Let's write a generalized equation. So this is not the problem that we're doing, but we're going to go back and write a generalized equation. So if we had the generalized reaction A for the reactant and little a for the coefficient, plus B, capital B, and little b for the coefficient, makes little c, little c is the coefficient, plus little d, capital D. So here we have the products. The coefficients are shown with the lowercase letters, the concentration with of each product with the capital letters. The equilibrium expression, which is shown with the symbol Kc, so the equilibrium constant, Kc, is equal to the concentration of the products, so that would be C, and brackets mean concentration. Brackets mean concentration in molarity, moles per liter. So the concentration of the products raised to the power of the coefficients multiplied together, all divided by the concentration of the reactants raised to the power of the coefficients of the reactants. So this is our generalized equilibrium expression. So we can apply that now to this expression, and we can write an equilibrium expression for this equation. Kc and for this is H, the concentration, multiplied by the I2. And these are both coefficients in front. Do for that question. Let's look at this second example. What if we have CH4 plus HO and 3H2? So the equilibrium constant expression, Kc, and if you'd like to try this one on your own, you can pause it and we'll go over the solution, is CO times H2 raised to the third power divided by CH4 times H2O, and there we go. Now we can also go in reverse. So what if we have this problem? So what if we had the example, so if we are writing the balanced chemical equation from the equilibrium constant, for instance, Kc is NO2 over times O2. So with this expression, we could go in reverse and just reverse the process. We know that the products are on the reactants are on the bottom, so we're going to have NO. The 2 is the coefficient 2NO. Now, gas states of matter in this case, and the state of matter we're going to see in a moment is important. It affects equilibrium. So we're going to write gas for each of these. Plus O2, coefficient is 1, produces NO2, and the coefficient for that is 2. Alright, so let's look at some other applications of equilibrium expressions. First of all, what if we have something more than just gases, as we saw in the last example? So in this example, we have heterogeneous equilibrium expressions. So that would mean heterogeneous, we have different states of matter. And so that has an effect. Let's do this first example. So we have CO plus 2H2 makes CH3OH. All right, so we have carbon monoxide plus hydrogen gas makes methanol. So in this example, carbon monoxide is a gas. The hydrogen gas is a gas, of course. But the methanol is a liquid. So that has an effect. Now, gases can change in their concentration. We can illustrate. Gases, for instance, can be compressed. If we have gases in a cylinder, and that cylinder compresses the gases, so that increases the concentration. Maybe it was 1 mole per liter here. Now it's 2 moles per liter. The concentration has changed. Likewise, things in aqueous solution can change in their concentration. So we can have, for instance, maybe a gas here and gas dissolved. Well, by increasing the pressure, various factors, we can change the concentration in solution. So maybe we had, once again, 1 mole per liter. Now we have 2 moles per liter. So things that are dissolved and things that are dissolved in solution, so that would be aqueous solutions, and gases can change in their concentration. Things that are not in solution or gases, like for example liquids and solids, these do not change in their concentration. So if we have pure liquid, as long as the density is the same, 1 gram per milliliter in the case of water, if we add pressure, if we change the temperature, the concentration doesn't change. Likewise, solid, if we have a hunk of solid in a container, the concentration remains the same. In the equilibrium expression, we don't include solids or liquids. So we can make a summary here. Included would be gases and solutions not included pure solids and liquids. And the reason why we don't include solids and liquids, although they have a concentration, their concentration will be as 1. So for that is because the equilibrium expression has direct equilibrium. And since, as happened, for instance, changes, solids and liquids don't change, we might as well not even deal with them. We'll just set their concentrations as equal to 1, and they drop out of the expression as 1s. So we will not include solids and liquids in the expression. So we set up our expression then in the same way. K, C is the products. Well, the product though this time is a liquid. And we just said that we don't include them, we set their concentration as 1. So we just put a big 1 there over the reactants, which is CO in brackets times H2 in brackets to the second power. And there we go. So let's do this next one as well. Have silicon plus 2 chlorine, L2 chlorine gas, silicon carbide, silicon chloride, SiCl4. So once again, the equilibrium expression, Kc, is the concentration of the products. It's a gas, so we can include that one. SiCl4 over the reactants. Now, in this case, silicon is a pure solid, and we won't include that. That just becomes a 1, and it drops out. But we do include the chlorine, Cl2 raised to the second power. And there's the expression. The last thing we're going to look at is the application or the calculation of the constants. So these are designed, these expressions are designed so that we can put numbers into them and we can learn what the constants are, and then we can use those constants, Kc values, to calculate other useful things. So we're going to calculate the equilibrium constants. So let's say we had this equation, H2 plus I2 makes 2HI. We're going to calculate Kc if H2 is 0.1 molar, I2 is 0.2 molar, and HI is 1.04 molar. Well, just a few extra steps here. We just need to put in first our write our expression. I'm going to write the concentrations though first off to the side here. So we have H2 concentration is 0.10 molar. We have I2, which is 0.20 molar. And then we have HI, which is 1.04 molar. And so we just write our expression. Kc is I raised to the second power over H2 times I2. And it's just a matter of putting those numbers in. So HI, 1.04, and I'm going to take the unit out, raised to the second power. all divided by h2, 0.10, times I2, 0.20. All right, now we just calculate that expression. Watch out for order of operations. We have to do the powers first before we can multiply or divide. So I would do this in my calculator as 1.04 squared, and then I would do divide by parentheses 0.1 times 0.2 close parentheses equals. Kc then is 54.08, and so to the sig figs, it looks like we have 2 sig figs based on these numbers, so or we could round that to 54. Now, something to keep in mind is the meaning of these numbers. So when this number is big, it means that the equilibrium is shifted towards the products, the right. When it is small, it's shifted towards the reactants. When it's about 1, around 1, that means it's evenly shifted in concentration. So if we looked at the last example, so if we have to work with, example 2, we have the equation 2NH3, ammonia makes 3 hydrogen moles plus 2N2. And again, we're given the numbers, and so we take the same approach. You can try this one on your own. We have NH3 concentration, which is 0.040 molar. We have N, which is 0.20 molar. We have H2, 0.60 molar. Just right plug them in. Kc is H2 squared times N2 divided by NH3 squared. So H2 then was 0.60 squared times 0.20 divided by 0.0, and that one is squared as well. Alright, we just calculate this, making sure that we're watching the order of operations. I'm going to do 0.6 squared, and then I'm going to multiply that times 0.2, and then I'm going to divide by parentheses 0.04 squared, close parentheses, and equals. Comes out to 45.